In 1948, Claude Shannon invented information theory in one paper. In 1951, he applied it to English and asked one question: how predictable is your next letter? The answer he got was 1.3 bits. That number set the entire course of NLP. Every language model since is essentially trying to beat that Shannon 1951 estimate. Today, what entropy actually is, why a fair coin equals exactly 1 bit, how Shannon measured English, and why Perplexity, the number your language model brags about on paper, is entropy in a costume. Last video I said probability is small. 6 concepts in log space. Today Shannon turns probability into something you can measure. Information. How many bits does an event carry? How many bits on average does a distribution carry? That single move connects probability to compression, to communication, to language modeling, all in 1948. The puzzle. If English were random letters, 26 equally likely, entropy would be about 4.7 bits per letter. But English isn't random. Q is followed by U 99% of the time. V is everywhere. So the real entropy is much smaller. How much smaller? Shannon literally ran an experiment on humans to find out, and got the answer: 1.3 bits. Today's 3 beats. First, what entropy is? The formula H equals negative sum of P log P, and the fair coin equals exactly 1 bit. Second, Shannon 1951, the prediction experiment on humans, how he got the 1.3 bits result. Third, Perplexity, the language modeling metric, which is just 2 to the entropy in a different costume. Beat 1, entropy. The formal definition: h of x equals negative sum over all outcomes of p times log p. Read that as, for each possible outcome, take its probability, multiply by its log, sum them all, flip the sign. That's the average number of bits needed to encode one outcome from that distribution. That's it. The canonical anchor, fair coin, 2 outcomes, each with probability 1/2. Plug in negative 1/2 log 1/2 plus 1/2 log 1/2. Log base 2 of 1/2 is -1, so it becomes negative of 2 times 1/2 times -1, which equals 1, exactly 1 bit. That's the definition of a bit, the information from one fair coin flip. Now the intuition. High entropy means high uncertainty. A uniform distribution, all outcomes equally likely, maximizes entropy. A spiky distribution, one outcome overwhelmingly likely, minimizes it. Entropy in bits also equals the number of yes-no questions you'd need on average to identify the outcome. 20 questions with a smart adversary. Log base 2 counts the questions. Beat 2. Shannon 1951. He wanted to know, how uncertain is the next letter of English really? He couldn't compute it from first principles. Nobody had a good English model in 1951, so he did what nobody had done. He turned humans into the model. Give a person a snippet of text. Ask them to guess the next letter. Count how often they get it right. The math trick. If a human gets the first guess right 40% of the time and needs a second guess 20% of the time, and so on, you can compute the average number of bits their uncertainty required. Shannon derived upper and lower bounds, ran the experiment, ran it on longer and longer contexts, watched the number DRLP as more context was given. Because more context means less uncertainty. The result? 1.3 bits per letter in the limit, which means English, once you know enough context, has only about 2 to the 1.3, roughly 2.5, effective choices per letter. Not 26, 2.5. That's how much structure there is in English, and it means, theoretically, you can compress English text down to about 1.3 bits per letter, no further, ever. Beat 3. Perplexity. The metric every language model is judged by, defined as 2 to the power of the cross entropy per token. That sounds intimidating. It's not. It's just saying, if the model's uncertainty is h bits per token, then the model is perplexed, as if it were choosing among 2 to the h options. Perplexity 100 means the model behaves as if the next token were one of 100 equally likely options. So when a paper brags we cut perplexity from 40 to 20 foot, they cut the model's uncertainty by 1 full bit. In Shannon terms, they got closer to the 1.3 bits ceiling. Lower perplexity means less uncertainty means a better model. Every language modeling benchmark for the last 30 years has this metric on the leaderboard. It's just entropy in evening wear. The reason Shannon 1951 matters 70 years later, it's the theoretical floor. Human-level language prediction lives at 1.3 bits per letter. Modern large language models are now brushing up against that number on English, which means we've reached the limit of what's compressible. And any further gain from a bigger model has to come from something other than raw prediction accuracy, reasoning, tool use, not more compression. 3 takeaways before the quiz. 1. Entropy is negative sum of p log p. It's the average bits per outcome. Fair coin equals 1 bit. 2. Shannon 1951 measured English at 1.3 bits per letter. Humans as the model. 3. Perplexity equals 2 to the entropy. Lower perplexity, better model. Every leaderboard chases the Shannon floor. Quiz 1. What is the entropy of a fair coin? A 0 bits, B half a bit, C 1 bit, or D 2 bits? C. Exactly 1 bit. 2 equally likely outcomes at probability 1/2 each. Plug into the formula. Log base 2 of 1/2 is -1. Everything cancels to 1. That's literally the definition of a bit. The information from one fair coin flip. Quiz 2. What did Shannon's 1951 experiment measure about English? A. The size of the English vocabulary. B. The uncertainty of the next letter given context, about 1.3 bits. C. The number of words per sentence. Or D. The average length of English words. B. The per-letter entropy of English, about 1.3 bits given enough context. Shannon used humans as the language model, asked them to guess the next letter, counted attempts, derived bounds on the entropy. The number is the theoretical compression limit for English. Quiz 3. How is perplexity related to entropy? A perplexity equals entropy times 2. B. Perplexity equals 2 to the entropy. C. Perplexity is 1 over entropy. Or D. They're unrelated. B. 2 to the entropy. If your model has h bits of uncertainty per token, it's perplexed as though it were choosing among 2 to the h equally likely options. Perplexity is entropy in evening wear. Every LM leaderboard reports it. Back to the puzzle. Shannon turned probability into information. He gave us entropy, a way to measure uncertainty in bits. He measured English at 1.3 bits per letter, and he gave us perplexity, which is how we still evaluate language models today. But how did we build those models before neural networks? By counting. Next video, n-grams, the classical language model, still in your phone keyboard. Next time, n-grams. Before GPT, the dominant language model was just counting which words appear after which other words. For 20 years, best you could do, and it's still in your phone's keyboard. Hit subscribe.